Guys, let's get started here. So this is lab 8, and on this lab it's actually going to be something a little bit different from what you guys have been doing before. The first thing we're going to look into two new technologies. One is AWS, or new to some of you, I guess. The other one is Vagrant, and then lastly Spark. So we're going to move a little bit away from the sklearn stuff, although we'll come back to that later on. The way that this is going to run, the lab itself, is I'm going to start showing some of the AWS stuff. And then we're going to have Richard show the Spark, and, I'm sorry, the Vagrant, and then the Spark thing. And you'll understand why we're actually using Vagrant. OK, so AWS, for those who don't know, is the Amazon offering for you to use their own platform. So it's the stuff that they use to serve their content. And at the beginning of the semester, we told you to apply for a student or for an academic license for or I should say credit for AWS. And if you did, you got about $100 worth of credits for AWS. You're going to need that money. You're going to need to use that money because although there is a free tier on AWS, that free tier does not work for the stuff that we're going to need. So we need a little bit more powerful machines, and the Ec2 instances that you can get for free, they can't support what we're going to do. So again, just to remind you, if you have not applied for those credits, apply as soon as possible. If you have any problems, just contact us. But it should be pretty straightforward. And again, you should have that by now. Cool. So the initial part will be to, either sign up or sign into your account. Let me just sign into mine. And your signing process will not be as complicated as mine. But OK, so this is the AWS console. So it goes over a bunch of different services that AWS offers. And actually, some of these might be useful for your project. The ones that are the most important to us are going to be Ec2, which is their virtual instances. That's how you create virtual servers on AWS. S3, we're going to use not this time, but on the next lab, in the next homework. You're going to use S3, which is just a data store on AWS. Not the same as your hard drive. It's actually an object store. But in any case, it's easy to use. I think there's 5 gigs of free data, or 1 gig, something like that you can use on S3, so pretty useful. We're going to use the IAM, but we're just going to do it one time. We're going to do it today, and you're never going to have to worry about that again. And also, last but not least, what's important to us, which is EMR. So EMR is Elastic MapReduce, and this was originally the Hadoop framework on AWS. Now it offers Yarn, which is Hadoop 2.0. It offers more than MapReduce. We're going to actually use Spark on top of EMR, which will make our lives easier. But again, there are a lot of other interesting services here that you can use for your projects. If you have any questions, you can contact one of the TAs, or at least me. I should offer myself, not the other people. And I can go over some of this stuff because it might help you with your projects. Cool. So here's the initial thing, as I said. You would log into that service and create your account. And then the next step will be to actually go to IAM and create a user for us to use during the lab itself. Now, the way that this works is that even though you could use your username and password for all of the functionality inside AWS, that's not secure, and it's not the recommended way. So ideally, what you would do is go in and then create another user inside the IAM service. And this user would actually be the one that would perform all the actions for you. So here's the idea. You would go into this, go to users. I already have everything created, but you would then create new user. Straightforward. Just put the name here. Actually, why don't I do this now? Let me delete mine. So create user. We'll call it CS109. Create. And all these instructions are on the lab manual. The important thing here is this. You're going to receive this access key and secret key, and you're going to need to have them for the lab. So you can copy and paste from there, although if you just click this button, it will download the CSV file with those credentials. In any case, they're here, and I just realized that I did something really dumb, because now my old stuff not going to work. So in any case, so let's close this and keep going. Okay, so now we have a role created. The next step that we have a user created. The next step is actually to assign the right permissions for that user. And that you can do here on the user itself. So if you click on the user and you say attach policy, and straightforward, we're just going to search for administrator. It's the first one, but I just want to show you how to do it. Just put admin there, and you select administrator access. So what we're doing now is just we're giving that user administrator permissions on that box. All right, and that's it. So now you have a user, you have the credentials, and the next step is to actually create Ec2 Ssh Keys. So these keys are going to be used for you to remotely connect to the Ec2 instance. And you're going to need that because basically at some point we're going to start running the IPython notebook directly from AWS. So this is the next step, and it's pretty straightforward. The idea is you go back in here, click on the little orange cube, go to Ec2, and click on this button, key pairs, or it should say option. I already have the key there. This is even easier than before. You just say create keys, give it a name. The name that we're using on the homework is just CS109. And then you click create. When you create the key, it's actually going to download it to your a PEM file to your machine. And one thing to keep in mind, this is the file over here. Let me open my folder. So this is the file, CS109 PEM. For some reason, if you do it from Safari, and I don't know if other browsers behave the same way, it's actually going to attach another extension here, .txt. So just be sure to rename the file and just leave the PEM, just because all the instructions use that. It's actually, if you know how to adapt the instructions, that's fine. You can just use the full name with the txt or whatever it names. But the instructions actually just have it with .pem. So if it adds anything else, just rename it and leave it with the PEM as the last extension. Cool. All right. So now you have the SSH key and you have the user that you need for the lab. And the next step is going to be to actually download something called AWS CLI tools. So there are a bunch of different ways to interact with AWS. One is to use this console. The other one, which we will work with later on, is using Boto, for example, which is one of the APIs available for AWS. And that allows you to, from Python, create different instances and do a lot of different interesting stuff. We're not going to use Boto right now because it's a little bit behind the latest version of AWS, so we wouldn't be able to create the Spark cluster the way that we want with that. So we're going to use the CLI to do all the other stuff. So we have the link on the notebook. All you have to do is come in here, come to this page. There are instructions to installing it on Windows. There's also instructions to installing using pip. I don't suggest you do that, even if you have Linux and OS X. I suggest you actually go to the OS itself and install the CLI directly. So you download it, install it, and you're good to go. Cool. So next step is once the AWS CLI is installed, we're going to run the AWS Config command. And I believe that's the name. Let's see. AWS Configure. So AWS Configure. And this is going to ask you for the key that you downloaded before. So in our case here is actually the number 2, because I had another one before. And this is the key. So this is the access key ID, which is the first thing that it's asking for. And the secret key. For the default region, we put on the instructions. You're going to be using US East 1. So I'm just going to leave mine because it's already configured. And for the default output format, I like JSON. You can change something else to text. But JSON, I think, is the best format for now. That's it. So now you have AWS tools installed and configured. And we're going to go on. OK, so now we're ready to actually create the Spark cluster. From now on, all of the commands that we're going to use, you're going to have everything in here. Later on, I'm going to show you some things that are going to change a little bit, where you're going to have to put your own information. So for example, your own key name or that kind of stuff. But for now, this is what we're going to use. So all you have to do is copy this thing and paste it on the command line. And actually, let me just open a new thing. And there you go. So if it worked out, and it did, you would just get this JSON output saying the cluster ID and then this thing. You need to save this somewhere because you're going to need it to terminate your cluster later on. But basically, that's just an information on what the name of the cluster that you created is, or I should say the name, the ID. If you do want to go back to the console, you don't have to do this, but if you go back, you see that the Spark cluster, I have a bunch of them here, but you see that the Spark cluster, which is the one we just created, is actually starting now. Cool. So the cluster that we created, and you can see from the command line, is going to be one master node, which you need for every cluster, and then we have two core nodes, and they're all using the M1 medium EC2 instance type. So this is not the box not too beefy, which means it's not too expensive for you to maintain. So it can be on for a few hours. You definitely, if you follow this and just go through the homework, you're not going to get even close to the $100 that you have. But and let me make this very, very clear. It's on the homework, and we got to remind you, you have to terminate your boxes once you're done with the lab. You may restart those boxes later on, but if you leave those things on, they're going to Amazon's going to charge you per hour of use or per hour that those things are on. So again, terminate your boxes as soon as you're done with the things that you need to do here. Reprovision them if you need to, and they're easy. We can rerun this again, but you have to terminate things. I might say that a couple more times because you really got to do that. Every time, we get people complaining that they were charged hundreds of, even more, for forgetting to turn off a machine. Okay, this is going to take a while. The provisioning actually takes some time to get those machines up and everything. So I'm going to switch now, and we're going to talk a little bit about Vagrant and Friend. So, Richard, here's your thing.
So I'm going to be talking about Vagrant and Spark. So for this week, we're going to make you guys install a lot of things. We're going to have you guys install AWS stuff, as well as Vagrant, Spark, and VirtualBox. Shoot. Okay. So the reason why we're using Vagrant and VirtualBox is because installing Spark on your local machine can be really cumbersome. Configuring, especially in Windows, can be really difficult. So what we're going to do is provide you guys with Vagrant, which is a virtual wrapper around a virtual machine like VirtualBox. And we're going to install Apache Spark in there for you guys so that you guys don't have to go through the process of installing Apache Spark by yourselves. Right? And this Vagrant virtual machine will be using 2 processors and 1 GB of memory. So it would be a pretty good idea to close down and turn off all the other work that you're doing when you're running Vagrant. Also, we're going to be using port 8888 to interact with the virtual machine. So if you have other IPython notebook open, it will have a port clash. So it's a good idea if you have other homeworks for other class open, just close that down and leave the port open for our Vagrant. All right, so first step is downloading Vagrant, and this step is pretty intuitive and straightforward. So just go to their website and download it for your operating system. And also, you're also going to have to download VirtualBox. This is the VM. It's very straightforward, so I'm going to just skip these steps. So inside the lab, for lab 8, you're going to see this file called Vagrant file. This is our Vagrant script. This is where our Vagrant script lies. So change your directory to 2015 Lab 8, and then type in Vagrant up. Now, once you do that, the Vagrant will start installing Anaconda distribution, Java EMR, and Apache Spark. And the first time you run this, it can take up to about 25 minutes to even 30 minutes. But after you do Vagrant up for the first time, the second time up, this should probably take less than a minute. It won't have to reinstall all these distributions again. And then that's it. Okay, so once you've done that, open up your web browser and type in localhost 8888 tree, and you should see a page that looks like this, right? So here's a lab, and these are Anaconda and Spark distribution. Open up the 2015 Lab 8 folder, and you should see something very similar to this. We may have to update this folder, but yeah. So this folder has been synced to your local directory, 2015 Lab 8 directory. So what you're actually seeing right now here is the page that's being displayed through the virtual machine, but it's been synced also with the local 2015 Lab 8 folder. So any changes that you make,
the system is on the Linux box inside your virtual
inside, so any changes that you make here will be also reflected in your local machine. So you don't have to make duplicates, upload, download, things like that. Oh, and also, so okay. So you could open up your notebook and do your work, save, and then when you're done, like you need to shut down. Actually, please ignore the first line here. As I'm saying, I'm gonna update this. This is kind of older instruction. So when you're done, just type in Vagrant halt in that same directory. So this will shut down the VM. So it's not as scary as AWS situation, but if you don't halt, that Vagrant will be alive and will eat up your cores and your memory. So in order to release them, you need to do Vagrant halt.
And you're running this on your Mac or your Windows machine?
Either one will work. Yeah. Okay. So let's move on to examples in Spark. All right. So let's just say that we provisioned Vagrant and
Go to command line and start Vagrant.
oh, is it up already? Well, the thing is, I don't know if I want to actually go through the code itself. I'm just gonna show the code outputs. So we're using this library. It's already inside your Vagrant virtual machine. Library called Find Spark, and this is gonna make it really easy for your IPython notebook to interact with Spark context, right? And it will find Spark and Spark context, and using PySpark, you create a Spark context, name it SC. For first example, we're gonna go over like a really simple example of estimating pi. So we're going to use Monte Carlo simulation, and so let's imagine that we have a unit square like this, and that we're throwing a bunch of millions of sand particles in there, right? And we're going to count up the number of sand particles that land inside the quarter of the unit circle here, and divide up that number by the total number of sands that we threw in. And we multiply it by 4, and we're going to get an approximation of the number pi. So how we do this in Spark is first we create a function. Here I just call it sample, and it's going to draw a random number for x, a random number for y, and it's going to determine true or false whether or not x squared plus y squared is less than 1. Now in our lecture on Spark that Rahul is going to do, we're going to learn about RDDs. And what we're doing here is sc.parallelize range n. We're just creating an RDD, a collection of integers from 0 to some number n. In this case, 1 million. And what we're doing is mapping a function, the sample that we created, the sample function that we created, to each integer in that collection in RDD. So we're creating a sample of true and false, 1 million of them, and then reduce. We're going to reduce all the collection of the true and falses, sum them up together. If we do this, so in this particular case, in virtual machine, it can take a little longer than if you do it on your local machine. We have an estimate of 3.13, which is not really great estimate. It took about 13 seconds. And the actual NumPy estimate of pi is 3.14. So it's not perfect, but if we increase this n here, let's say to 100 million or billion, we could really get a good estimate of pi. But at the same time, that will cost us runtime. So this may go up to a minute or 2 minutes. Okay. So in Rahul's lecture on Spark, we've gone over word count, right? You're doing word count, right? Yep. And I'm going to kind of extend that and explore what's this thing called Zipf law. So Zipf law states that the frequency of the word. Let me kind of read this. In linguistics, Zipf law states that given some text of natural language, the frequency of any word is inversely proportional to the rank in the frequency table. And we got so the most frequently occurring word will occur about twice as much as the second most frequently occurring word, and it will also occur 3 times as much as the third most frequently occurring word. And here is the Zipf distribution that characterizes that law. And what we're gonna do is we're gonna take a bunch of text from Project Gutenberg and see if this is true. Okay. So first of all, let's take a look at the Zipfian distribution, the probability mass function. So this is how it looks like. And interestingly, this Zipf law, is primarily studied for languages, natural language, but it has been found to be kind of true in ranking of the size of the city by population. It's also been found to be true in the ranking of U.S. firm by revenue size as well. So there's a website called wordcount.org, which already demonstrates the Zipf law. So it takes the British National Corpus, which has 100 million words in it, and it keeps track of every single word that's in there, and tracks the distribution of it. And we see here that the is the most frequently occurring word, of the second most, and so forth. And the frequency follows the Zipf law. And what we're going to do is we're going to replicate wordcount.org's example with text from Project Gutenberg. So what I did was I downloaded 16 texts from Project Gutenberg. And many of them are kind of older novels. So their lexicon might not be exactly the same as the modern day English. But otherwise, I think it's a fairly good representative of the English language. We're going to parse all this text, which has over 2 million words, and then plot the Zipf curve based on it. So we're going to start by creating a function called parseWord. So much similar to what I did with sample in the Monte Carlo simulation. You first create a function that you're going to use to map to your RDD. And this parseWord is going to go in there and take a sentence like this, sample sentence, and it's going to parse it. It will eliminate punctuation marks like commas and periods, question marks. It will return all the words to lowercase. So words like, capital letter bank here and little smaller lowercase letter bank here, it won't be captured as a different word. So let's test it out on sample sentence. It's a line from Alice in Wonderland. So here it is. Okay. So we're going to load up those 16 text files and convert them into RDD. Spark Context has this great method called text file, which will automatically read in a text file and convert it into an RDD. that's what we're doing. Iterating through all the text files in this folder called data, and we're appending, or by a method called union, appending them to create a big, giant text file RDD. I'm going to call it text RDD, and here's the result. I'm just taking the first 20 lines here. It sort of looks like, when you print it out, it looks like a Python list, but it really isn't Python list. So on this, just looking at it, you would think that it's a list, but it really isn't. It's completely different features and properties and methods. Okay, so there's a method called map. In our case, it won't work. I wanted to demonstrate this while I'm walking through this actually coding, but if you do parse word, you pass in parse word into the map method, we're going to see what happens. So you see that it has created an RDD, it returned an RDD that sort of looks like a list of a list, with each element being a word. This is not quite what we want. What we want is an RDD of each individual word, not a list of words. So fortunately, there's a method called flatMap, which will do exactly the same thing as map, but it will flatten the result and return back another RDD. So we're going to use that one. So here's the result. So this is what we wanted, right? Just list of, or RDD, collection of words. Okay, we're going to take that and we're going to see, okay, how many words were there? The total number of counts, not unique counts, but total number of words. And we see that we have over 2 million words here. This is actually bigger than the Brown corpus, one of the famous corpuses out there in linguistics. And we're going to take this and take the word RDD and convert it into a key value pair, sort of like map reduce paradigm that you guys seen in a lecture before. So you're simply taking each individual word and turning it into a tuple of word key as a key, and just simply one, numerical number 1 as a value. And that's word pair RDD. Let's take that word pair RDD and apply reduce by key method and sum up all the numbers, the ones next to the words, right? So we've seen this in word count and map reduce. You're doing shuffling. Reduce by key would shuffle and sort based on the words, and sum up the occurrences of ones that were returned as a list of ones, and we're summing them back up. Okay? So this gives us, we can now get the count of unique words. We have over 56,000 unique words in our corpus. Okay, so we're going to order these counts by descending order and take top 50 words. So we can already see here that the and of that we saw in wordcount.org website are represented as top 3 words here as well. Okay, so this is what happened in steps. We created a text RDD that are a collection of lines, of strings, transformed it into word RDD, which is just simply a collection of words, then again transformed it into word pair RDD, keyed by a word and value of 1. Then again converted to word count RDD. Then finally we got top 50 words, which is not an RDD. This is a Python list. Now, we did this in steps to demonstrate each individual methods, what they do. But in fact, they can all be done in one line like this. And this is chaining. So you start from text_rdd.flatmap. Now, Python doesn't let you do indents unless you're inside a function. But you could bypass that with a little hack where you put them around parentheses. So we didn't really have to do all that. We just could have done it in one step. I just wanted to demonstrate what I was doing. So let's visualize this. Here it is. Here's our result. So here's the ZIF distribution and our sample distribution of words from our text. So again, similar to what we saw at the top, word count org, the is the most frequently occurring word. We see that and of have been switched. But otherwise, this distribution of words from our sample follows a Zipfian distribution almost perfectly, with the exception of the. So it's not perfect, but I think if we had a much bigger corpus, I think we could have hit the ZIF distribution closer. So anyways, for those of you guys who actually are proficient in another language, I think you guys should try this at your own time, in your own language. So, and if you can, like, post the result like this on Piazza. If you know Chinese or Spanish, I think it would be kind of cool for your classmates. And to learn more about Apache Spark, please go to documentation. And there's tons of examples in Apache Spark's official GitHub repository, so go through those. I think that Nelson's AWS cluster is now up, so I'm going to pass it over to him.
All right. Put this back on. All right, cool. So before I actually go back to the cluster, I want to talk just a little bit about why we're doing all of this. Because you might be thinking that, well, you could have done all of this on your notebook with just Python. You don't need Spark. You certainly wouldn't need AWS for this kind of stuff. So the idea here is, and you guys are going to go over MapReduce later on in class. Yeah. But generally, at its simplest, you have on a regular MapReduce cluster, something like what Hadoop would do, or kind of what we're doing with Spark. The idea is you have an input that goes into the mapper. The mapper splits that input into a bunch of different things and does some very basic calculation on it. And then these inputs go back into the reducer, which, again, generally will just return one thing back to you. Cool. So the problem with this approach is that, first of all, when you're using Hadoop, for example, the problem with this approach is that when you get that output's actually written back to disk. So if you need to use it for something else, you need to refeed it into the mapper, which will then redistribute everything and load it from disk to memory. And usually your mappers are distributed on different nodes of your cluster. So what's going to happen is that output's going to have to be redistributed and all of that. You're going to notice that when you run these simulations on your AWS cluster, it's going to be slower than when you run on your box. That's because there's a lot of latency with these steps of actually getting that data into all of the nodes, in this case just 3 nodes, but copying the data. There's also a bunch of services running that do the mapping, the reducing, and everything else. So the idea of Spark itself is that it eliminates this part of actually writing things back to disk before you can process it again. Spark allows, and it runs on top of Hadoop, or Yarn to be more exact, but it allows you to basically reprocess the data while it's still in memory. And that's very important for most of the stuff that we're going to use. It's certainly very important for machine learning, because you usually care about getting the output of a reducer and then rerunning again through something else. Maybe, I don't know if with MR job you guys are going to do this, but there is a way to chain Hadoop jobs. But again, the problem with that is that it touches disk first, and then it goes back all the way to be redistributed to all the clusters and all. And you can imagine if you had hundreds of nodes in your cluster, that's a lot of overhead. So there's a lot of latency inherent to the original MapReduce solution with Hadoop. So that's where Spark comes in. Now, the cluster itself, the way that it works, as I hinted at already, is that you have different machines processing different parts of your data. It's only interesting when your data doesn't fit in your memory. So if you have, even like an 8 gig file, if you have 16 gigs of memory, 32, which is normal on laptops or desktop machines nowadays, it's usually not worth to use a cluster. But if you have terabytes of data, then using a cluster actually makes sense. The way that it works is the master of the cluster will spread that data to all of the cores. So we created one master, if you remember, on AWS, and then two core nodes or slave nodes. And it will, basically, the master will distribute that data to the other core machines, which will then do the processing. They're going to be doing, the mapping. You can have cores doing just the reducing. So it's very flexible in the way that you can actually work things out once you have one of those MapReduce clusters, or a yarn cluster, I should say. So anyway, as I said, don't be surprised that this is going to run a lot slower on AWS than on your box. That's normal. We're just using this to actually show you how the technology actually works. But all right, so going back, you're going to see that my cluster now, the status of the cluster is waiting, which is good. It just means that now it is ready to receive commands and other things. So the next step that we're going to do is actually install Anaconda on the cluster itself. First step is we need to actually find out what the what the IP address of that cluster is. And the way to do that is with this command, which is also on your thing. And by the way, you're going to see the little not brackets, what's the name of the thing? Well, greater than, less than signs with some information inside. This is always going to be something that you're going to have to replace with some information that you got from a prior step. In this case, we got the cluster ID. Oops, sorry. Where's the? I lost the command where I launched the thing. But that's why I told you guys, save that information about the cluster ID because you're going to need it later. And I did not follow my own suggestion, but I can get it from here. Cool. So this command is just going to tell us what the IP address, what the DNS name is for that box. We're going to need that because we're going to SSH into that server to actually take the next steps. All right. Next thing is to actually SSH in. And again, as I said, you're going to have to replace some information. In this case, you're going to replace the DNS name with the information that you got from here. And you see that this is important. The PEM file, the file that we saved before. Let me make this bigger. Nope, that's not how you do it.
Command plus, I think.
Command plus. There we go. What happened? Maybe it's too big now. Okay. All right, cool. Anyway, so this cs109.pem file, let me just clean my screen, is the, sorry, I'm making him have a hard time with the camera. It's going up and down. But this is the file that you saved before. So this is what you got from the EC2 SSH steps. Ideally, you just put that inside your lab 8 file, your lab 8 directory. Yeah, your repositories are private. So that's not a problem. You can leave that key there for now. Eventually, you can never make your things public.
It's not private though, because they typically fork it.
Oh.
So you should keep it outside somewhere.
That's true. Okay, so forget that. Keep it outside. So let's keep, for example, I have a copy of that on my downloads box, download folder. So not a big deal. You don't have to. The only thing you have to do is actually put the path to that. And on the notebook, we actually have the instructions for Windows people as well. So, which is a little bit different because you're going to be using PuTTY instead of this. Okay. Downloads / All right. Cool.
This might work directly on the shell for Windows people because Git on Windows does install Git bash.
There you go. If you can hear that, what Rose said is that this might work for the Windows people as well because the Git, when you did the Git installation, it actually installed the bash for you. So it might just work.
So you use the same command line
Yep.
on Windows.
Cool. So we'll double check that, make sure that it works, and then we'll update the instructions if needed. All right, cool. So that drops us inside the the master node of our cluster. This cluster, of course, doesn't have IPython notebook installed. I'm sorry, Anaconda installed yet, so that's what we're going to do next. Because eventually what we're going to do is run those same commands that we ran on the outside inside the cluster. The one thing to keep in mind that I kind of glanced over, but with the command that I used to actually log into the server, there was an extra little string over here. This -L8989 localhost. All this is doing is it's creating a tunnel. You're going to log into the box, and at the same time, it's going to create a tunnel to this box over SSH. So basically, that's going to open a port on your local box on port 8989, and that's going to connect to the local host, which is in this case the Ec2 cluster, on port 8888. So if you can imagine that what that's going to achieve is you're going to have a direct connection to your cluster. All right, next step will be to download the Anaconda installer. We'll do that now. And then once that's done, we are going to install the thing. So while this thing is downloading, just to give some background, the Ec2 instances, in this case, they're Linux boxes. If you're a Linux person, they're compatible with CentOS. They're actually AMI, the Amazon something images. But they're based on CentOS, Red Hat. So they use the yum command and that kind of stuff. So if you need to install anything manually. Cool. And now we're just going to install the Anaconda. Hopefully you've done it before, or else you wouldn't be able to do your homework or anything. So, and that's it. So let's install. It takes a few minutes to finish up. And then I'll just go over the next steps that we're actually going to take. So once that's installed, we are going to copy the notebook that we have on our local box. We're just going to copy the whole thing to AWS. It's going to be the command. Oh, I need to update this because this is the IP address over here would actually be your IP address, the one that your DNS name, the one that you got from the previous step. So let me just update this really quickly. DNS name. Doesn't make a lot of sense, but okay, cool. All right. So, as I said, what we're going to be doing here is once the notebook is installed, we're going to do the same thing that Richard did on localbox, which is just run that Spark, the Spark job. But instead of running on your local machine, or in our case, it was actually running on Vagrant, which was a virtual machine on your local machine, we're going to be running this on the EMR cluster over AWS. And again, as I said, this is going to be when you actually run this is going to be a lot slower than when you run it on your box, which is expected. This is more interesting when you actually have a lot of data to process. Cool. While that's happening, we can actually start the copy, even though that other thing's not done. So just open a new shell over here, and it's just going to copy the file to there, although I need the IP address here, or the DNS name, using IP address. Okay. All right. If you haven't used SCP before, it's part of the SSH suite of programs, and it works the same way. Where you have you pass the where you want the key that you want to use. In our case, we pass the file that we want, and then where we want to copy it. Again, all you have to worry about is to copy and paste this from the notebook and update the DNS name appropriately. But there we go. It just copied everything there. All right. Let's see how there you go. So Anaconda's done. And now we're just going to run the IPython notebook and hopefully be able to connect to it. Okay. So it's just complaining about some stuff. Don't worry about this. And let's see if I go to localhost 8989, which was the port that I forwarded to. There we go. Oh, no, hold on. That's my port. Which port did I forward to?
It should be in your SSH
Yeah.
command.
Yeah, it's here. Should be here as well. Oh, my mistake. I actually my own version is actually running on 8989. Let me cancel this. This is not good. Okay, so I'm going to just log out of the thing and change the IP address because I already had another instance running. So logging out, and instead of 899.89.89, I've just put 8999. And same thing, just go back in. Don't worry though, for your stuff, when you're following these instructions, you shouldn't have to worry about that. Okay, let's go back here and 8999. And there we go. So you can see that it's different. It's different from this is what my local one looks like, and this is what the one remotely looks like, on the remote looks like. And this is the notebook that would actually run on the other box now. Now, you can then run all of these commands, well, once you copy everything over, and if you follow all the instructions, you can run the commands that we have on Richard's notebook. You can actually run everything in there as well. It will give you the same results. And that's it. So you create your first Spark cluster.
So, but this is still not running on the Spark cluster, is it? It's running on the local machine.
No.
On Amazon.
That's the master. Oh, that's the master cluster on the Spark machine. So when you call the context on that, we didn't create a new EC2 box to run this. This is the master node on that thing. So when you call the Spark context on that, it's going to be the Spark context that is configured to use the cluster itself. So this would run on the cluster.
If you use find Spark on the cluster,
yep.
It's going.
Well, in this case, I have to use the find Spark. It's not there. It's actually here.
If we run this.
I need to install find Spark there. Sorry. Pip install find Spark. I actually need to install Seaborn as well. All right, cool. And I need to run this. So this will find the Spark context on the local box, which is the master of the cluster. So you'll run the job on the other two nodes because so it is configured. Where is it? Spark itself is configured to do it from there. I mean, one way to see this is actually if you start the what is it? Spark shell. And if you run things on the Spark shell, it will also run on the things. But this is, of course, this is not Python. This would be Scala.
So you can run the PySpark shell directly on the command line.
Yeah, actually that's a good idea. Let's do that. So PySpark. Do I have to do ---- shell? No, just this. So just to give you background, once you have Spark installed, Spark actually has a Python API built into it. So what we're doing here is just we're running the PySpark, which is kind of, you can think of it as the command line version of IPython, or of just running Python by itself. But it has the Spark context, which is basically, you can think of, well, it's the Spark abstraction that works over the whole cluster. It takes a while to start, so. Especially because it is in a cluster. So I'm wondering if these are just, no, they're not.
This looks like the logging.
Yeah, have you ever run the PySpark before, the shell?
Yeah, it stops. The stuff doesn't show up after a while.
Okay.
We can figure that part out.
Yeah. So well, basically the idea would be once you run, you don't have to worry about this. Once you run the notebook itself, the notebook will be on the Spark context, and you'll be able to do all this fun stuff without having to worry too much about it. So, is there a simple like, SC? I think we can get the SC information from here. See that. I don't think there's anything here that can actually show us the that you're actually running on the cluster, but yeah, whatever. This thing's still running, right? Yep. Yeah, I don't know what's going on with that guy, but yeah. So the idea is once you run this thing, once you run the notebook, you're good to go. Cool. So that was it. Just to recap, what we did was we started by setting up AWS. We created the user, or the user that's going to be used for these things. We then created the roles that were going to be needed to actually create the Spark cluster. And then lastly, Richard actually showed you how to use Spark itself. And we decided to go with a local virtual machine solution just to make it easier for you guys to install Spark, because it's not that simple to install locally. And then we finished configuring the AWS cluster so you can actually run these things directly on the EMR cluster. And that's it. So now you're good to go for Lab 8. Thank you.